Okay, so welcome everyone to this webinar about the GHOST project towards next generation design tools for geothermal energy systems. GHOST is a project funded under the Geothermica program. And before starting, I just wanted to say that you can use the chat that will stay open until the end of the webinar. So you can just submit your question through the chat in the Q&A session here. And then we're going to reply in the end of the webinar. And also, if you want, you can also ask to speak, so I can open your microphone if you prefer. Before starting, I'm going to introduce the speakers of today's webinar. So we have 5 speakers. We have Robin Mutschler from Empa. We have Emil Martini from the European Geothermal Energy Council. We have Matthias Sulzer from Empa, Michael Vetter from LBNL, Alireza Afshari from Aalborg University, and my name is Alessandro from Aalborg University as well. I think from my side, the introduction is complete. So I will leave the floor to Robin for the first presentation.
Okay, thank you, Alessandro. I think you have to take your presentation down so I can put mine up. Okay, so also welcome to from my side to the first webinar of the GHOST project. So the GHOST project stands for Geothermal-based Optimized Energy Systems. And in this webinar, we're going to see what we mean with it, and we're going through the different layers of the energy system. The GHOST project is funded under the umbrella of the Geothermica framework and also in collaboration with AirNet Smart Energy Systems. And we are very glad that we have this format also for an international collaboration. So as you can see, we have quite an international consortium with European partners and also with partners from the US. So this is our team at the kickoff in January in Switzerland. So here in front of the Nest building, where we also in the background, you can also see the construction where we have on the Empa campus a high temperature BTS storage site, which will also be used in the project. On the right-hand side, the picture of the GHOST workshop in Berkeley, where we also met to further develop the project last September. And also there on the campus, they have a geothermal storage site, which we are also using in the project to develop the geothermal integration further. So here, a brief overview on the involved people at the moment. This is, just mostly for the record. So what is the GHOST mission? So we want to connect the levels of the energy system, and we want to do it in a way that the different levels are connected. So far, a lot of research is going on in each of the levels of the energy system, from city level to the neighborhood, to the building, to the equipment, also to the underground level, so to the geothermal energy. But the integration, especially for geothermal energy, is a large challenge due to the different requirements on each of the platforms. But this will be the presentation of Matthias, who will introduce you to the platform-based design we're going to apply in this project. So our aim is the effective and efficient integration of geothermal energy into the energy system with a holistic view on the energy system. So the concept we are following is we develop from bottom up. So we have 4 pilot sites, which we are using to validate the so-called platform-based design approach, which Matthias will introduce. And these pilot sites also serve to validate the platform-based design approach. And in the final step, we are going to apply this validated and developed framework to different larger sized case studies, such as the city of Zurich or Vienna or Berkeley. Stop. Here we go. Okay, here's an overview on the different partners active in the different levels of the energy system. So we as Empa, we are focusing on the system integration and the platform connections. So with different methods, one, the platform-based design, the other mixed integer linear programming, as it will be later explained in more detail. In my second presentation, we have a focus on top-down energy demand derivations by also key performance indicators. This is performed by AIT. At KIT, we also develop top-down cooling demand and geothermal potential estimations. Together with an Empa spin-off Symphony, we also work on the system integration and in particular on a case study analysis of the Berkeley campus. And at Harvard University and Energy Machines, the pilot and case study coordination is performed, and also from Energy Machines we have valuable insights into real-world applications. At LBNL and UC Berkeley, they're specialists on the underground modeling using the TUF software and also other software tools, and also with equation-based simulation and control with the application of Modelica, where Michael will go in depth in his presentation later. Yeah, this is the GHOST project, so the geothermal-based optimized energy system with the project partners and also various project supporters, also from industry and also from public services or cities such as the city of Zurich. Okay, thank you very much.
Yeah, thank you, Robin, for the introduction of the GHOST project. Now the next speaker is Emil from the European Geothermal Energy Council, who will give an introduction and an overview of the geothermal energy in Europe.
Thank you, Alessandro. Thank you for the invite. I hope you can see my screen. So yeah, the focus of, well, maybe a couple of words about EGEC. We are the European Geothermal Energy Council. We represent the whole geothermal sector towards the EU institutions, especially. Among the things that we do every year, we draft what we call the market report in order to assess the status of the geothermal market in Europe. So the purpose of my presentation will be to show you some key data about the last market report we did, which collects data from 2022. And we are currently now drafting the new market report for the data of 2023. And it will be ready around May, June this year. So just to have a short overview of the geothermal sector in Europe. Currently, we have 145 geothermal electricity plants around Europe, which produce 3.5 gigawatt installed and more than 22 terawatt hour produced. As regards the distributing systems in operation, we have almost 400 geothermal distributing systems and new 14 new for the year 2022. And as regards geothermal heat pumps, at the end of the year 2022, we have more than 20 million systems. To start off with electricity, as many of you probably already know, the three big markets in terms of electricity, geothermal electricity in Europe are Turkey, Italy, and Iceland. You can see the development of this market in the last 10 years. As you can see, there were many additions in Turkey, especially, but Italy, despite not having had a lot of the new capacity in the last 10 years, is still one of the biggest markets. But there are a lot of emerging markets, especially, for example, Croatia and Germany, but also Hungary, and in general, Central Europe is quite developing on that, which are developing some new capacity in terms of electricity. Last year, we were celebrating the 110 years of geothermal powers. And we wanted to highlight some key features regarding that, especially in comparison, for example, maybe with other renewable sources. Quite outstanding fact is that we still have, for example, a geothermal power plant in operation since 1986. And in general, there are a lot of plants which are still running since the 80s and the 90s. And in general, about the geothermal electricity market, we have to say that it is now entering a new development phase. There's still a lot to do, but some new plants are to be put in operation in the next few years. And today, 43 projects are developed and 140 are investigated. Here you can see on the map, for example, the existing plants and the plants in development. So as I was explaining before, apart from the three big markets, Iceland, Italy, and Turkey, something is moving in Central Eastern Europe, especially Croatia, Germany, Hungary, but also Austria. And another thing to highlight about geothermal electricity is the importance of the capacity factor and the baseload feature, especially in comparison with other renewable energy sources. So as you can see, only nuclear is near our high percentages. But for example, if we compare geothermal energy with other like wind and solar, we can see that it's a great feature to have this baseload factor capacity in order also to be competitive in the market of renewables. As regards geothermal district heating projects, we have 316 new projects under investigations. And of course, Germany as is the biggest market and as one of the biggest market as the largest pipeline with more than 100 projects followed by France, but a lot of other projects are being developed in other countries, like for example, Netherlands, Italy, and Poland. As regard district heating, is also important to highlight the potential of the linkage between geothermal and agri-food. We have a lot of examples throughout Europe. Here we put, for example, the new project in Almeria in Spain to connect local greenhouses and agri-food production sites. So in the future, it will be more and more important to underline the linkage between geothermal and industry in general and agri-food specifically. In terms of market development, here you can see some further figures. So more than 300 projects are being developed or under investigations. In general, these are doublets with some also multiple wells example in some countries. And in comparison to the electricity market, as regards district heating, there are more countries developing projects. So we have examples in Serbia, for example, in Finland, Netherlands, Austria, and here you can see you have specific data for each country. In terms of resource and flow rates, here you can see on the map that most projects center on reservoirs which have temperature in between 60 and 80 degree range in the EU. Of course, we know since many years, so specific basins like the Paris basins or the one in Munich, which are which present quite good conditions for geothermal. But we need to have more resource mapping of this kind to discover all around Europe, which is the actual potential underground, because we still lack a lot of data in this sense. And in terms of trends, we highlighted in our market report that one of the current trends is also to have use of large heat pumps. So to conclude about the geothermal heat pumps market, you can see, for example, the comparison of the data from 2021 and 2022, because the figures of this last year were 17% higher than the year before. And in general, it witnessed the largest ever volume of ground source heat pump sales, with more than 140,000 geothermal heat pumps installed. And here you can see that we have the big 6 markets, both in terms of new sales and installed stock. So it's mainly the Nordics, like Finland and Sweden, but Germany remains, for example, the largest markets. But in the second graph, you can see that also other countries have seen increased in sale of heat pumps. Here you can see the number of installed stock, and Germany and Sweden are the biggest markets, also in terms of absolute numbers. So to conclude, maybe some projections and potential that geothermal can have in Europe. So we usually say that potentially geothermal could provide 20 until 25% of heating and cooling demand throughout Europe. We didn't mention cooling so far, but cooling is also another important sector to consider in the future. It could be also 10% of power generation, 50% of underground thermal storage. So also thermal storage would be something to highlight more. And last but not least, as regards the co-production of minerals, especially critical raw materials such as lithium. So 20% of lithium demand, because in the last few years we started to have lithium extraction for geothermal brine. So it can be quite an interesting market development in the future, also considering that lithium is critical raw material, and that the EU is investing a lot to have also extractions when possible of this material in Europe, rather than importing it from foreign countries. So that's all from my side. So thank you, Alessandro.
Thank you.
Back to you.
Yeah, thank you very much, Emil, for your presentation. And I think it's very interesting to see that there is a growing interest in geothermal technology, at least in Europe. I think we can keep maybe for discussion to see also if in the US there is a similar interest, but maybe we can keep this for later. Next speaker is Matthias, who will go into the platform-based design framework of the GHOST project.
Thanks a lot, Alessandro. It's a great pleasure to being here and give a short overview of platform-based design. First of all, platform-based design is not an idea or an invention of our team. So it's actually originated in the 70s. It helps digitalize the whole semiconductor industry, and later on it also revolutionized the automotive industry by coping with advanced systems. And we are also really happy that we have Alberto Sangiovanni Vicentelli in our team, who is actually the father of platform-based design. So you might now ask, why the hell they want to use now platform-based design in energy systems? I think we are facing a similar challenge as the semiconductor industry faced or the automotive industry faced decades ago. So it's maybe good not to actually start off from scratch. So really look in other industry. This is what we have done, how they actually successfully transformed their industry in a new world. And this is actually also our motivation to use platform-based design in energy systems to actually support the challenges of the industry. And one of the greatest challenges the industry is really facing is to decarbonize the system. So if we look at the IPCC report, and if we want to get the blue lines, that means we have to get net zero in 2050. I think it's really a task of urgency. So that means if you want to achieve that, just for the US has to actually retrofit 10,000 buildings every day, starting today, in order to reach that goal. Also for Switzerland has to retrofit, for example, 100 buildings every day, starting today, to reach their goals of net zero in 2050. So if we want to do that with the current workflow, with the current technique and method, I think we are struggling. So we have to really rethink the process of decarbonizing the energy system. First challenge. Second challenge, you might know that best if you are into energy system design, like a fossil fuel or the current system today is actually kind of a simple task. So it is linear to do the design. It's separated in their disciplines, and you can actually use simple tools, even like handcrafted tools, to find your solution. But if you look where we are heading into a more renewable energy system, it looks like this. So everything is connected, interdependent. And as I highlighted, part of that are also geothermal systems, which are playing a crucial part on the thermal side to support these decentralized systems, which are able to actually efficiently utilize renewables. So the second challenge our industry is facing is really how we manage complexity. And so if we want to do that, addressing urgency, addressing complexity with a handcrafted way, how we do it right now, I think we are struggling to achieve these goals. And here comes in our approach, or now in Ghost project, to test it out, how we can do that better, that we are structuring the problem not only in disciplines, really see the integrated part, but structuring the problem in different level of abstractions. This allows us to do decision making at the right time of the design flow. So you have high level decision making, maybe even on policy, on city level, and it is fully connected, these decisions, down to the component or even to the subsurface scale, which allows us to have a holistic, comprehensive design workflow. And having this structured in platforms, or having it structured in this level of abstractions, we can put that these levels into platforms. And on these platforms, this allows us to get in a fully digitalized workflow. I just mentioned on the left-hand side some tools which might help you to actually go through these platforms and finding the best solution on each platform with the requirements from the previous platforms. But these tools are just indication of possible tools. Platform-based design, it's really a workflow which is tool agnostic. You choose the best tools at each platform, and the challenge or the work, the research work, what we do is how we connect that in a seamless workflow from the very top to the very bottom part. So this is really in a nutshell what platform-based design is. And as you might recognize, looking a bit deeper into platform-based design, the most critical part is to actually structure the design problem in our case, the energy system with geo-coupled equipment into appropriate levels of abstractions. And as you see, you can do that on a scale of components to systems, to districts, to cities. So you have actually system of systems approach, like in the horizontal axis, but you can do that also on domains on the vertical path. So you might have domains on energy, but you have to connect that with the building industry, which is also affecting the energy system. And as you see, as more you actually move along the level of abstractions, you actually can integrate these systems and these domains into a high-level system. Again, what you see here, it's really this approach, how you can actually cope with system of systems. And this is, in my mind, the hardest task to do, then to fill up these platforms with tools and doing all these fancy calculations. This is really then the nice part to do, but the hard part, the brain work, it's really how you structure these platforms and how you organize these platforms. Last but not least, if you have built your platforms or defined your platforms, then, as I mentioned, gets into this lovely task to use tools to operate these platforms. You see that on the left-hand side, the most important part from connecting platforms are really these requirements. So each solution on each platform provides the requirements for the next lower level platforms. And this is actually the main connection between platforms. So it's the function itself is completely separated from the architectural solutions you can choose from. And this allows you in a really streamlined process and keeping requirements as important as they are, even on the lowest level. So you pass all these requirements and insights formulated into a new requirement to next level down to the implementation and operation. On the right-hand side, you see how you can actually use tools to actually support you to find the best solution out from the architectural space at each platform. And my colleagues, which actually will present some tools which we are using on, for example, on district and building level with MILP, Robin Mutschler, and also some tools which are more detailed, more refined, and more physics-based on the equipment level. For example, Modelica, which is presented by Michael Wetter. That's it from my side as a short overview of platform-based design. If you like to dive in, there's a paper, like a first paper, just outlining what might be platform-based design for the energy system. This is our very first paper on those, but we think we have to actually make them more detailed with the following on papers. That's it. Thanks a lot, Alessandro.
Thank you very much, Matthias, for the presentation. So we know a bit more about the platform-based design now. Next speaker is again Robin. So he will talk about MILP and the tools that can be used for optimization at the city or district level.
Okay, exactly, Alessandro. And thanks also for the great introduction to platform-based design, Matthias. So now we are going to dig into one of the tools we are often applying in energy systems and get an overview on how this also works together then with the level below, with the level above, and how this is embedded in the platform-based design approach. So the title, High-Level Modeling Abstraction with the Ehub X tool. So the Ehub X tool is an MILP optimization tool developed at Empa. So it's mixed integer linear programming, and we're focusing on the higher level of abstraction in the energy system. Okay, so this is the outline. We are going to discuss what the energy hub concept is, as you see it here in the figure of the paper Matthias introduced. So the marriage between the platform-based design and the energy hub as we apply it in the GOES project. Then we're going to discuss how to find the so-called optimal solution for a system via the mixed integer linear programming method. And we're briefly at the end discussing the benefits and limitations of this method, and then also the challenges and approaches we are following in the GOES project. Okay, here again a recap of the presentation of Matthias. As you have seen this slide, as was explained by him, you have the different levels. You can go with each step into more detail, and the levels I've highlighted here in red, these are the levels which you can typically model or represent with an energy hub, or and then also with a MILP optimization model. And here, again, a repetition of the slide Matthias showed. As he explained, we have on one side the requirements, and on the other side, then which are given by the functional space, and the other side, the architectural space, where we then apply the model. So for example, one requirement to a high-level MILP model could be, okay, we have to reach net zero in the year 2050. Our tool is then a MILP model, so the Ehub X tool, for example, and then with this requirement, we have to then find the solution which fulfills the requirement coming from the higher platform, for example, the policy platform. Okay, what is the energy hub approach? So here we see a representation of an energy hub. So we have classically on the left-hand side, we have the inputs. So this can be imports, cross-border imports, for example, gas from abroad, or this can also be the utilization of local resources such as wind or solar energy or geothermal energy, which we are focusing on in this project. On the right-hand side, we have the outputs. This can be export of commodities. This can be a demand which has to be fulfilled by the project, by the system. And in the middle, we have the energy hub with the system boundary, which is defined by the external requirements. And in the energy hub, we have technology candidates, which can then either be chosen or not be chosen. And this is then the beauty of the MILP method. So we do a holistic analysis of the system with all the technology candidates. For example, here we decide that we combine the import of an energy carrier with a conversion technology. We further convert it, and then we fulfill an export requirement. Or we use a local resource, we convert it in one step, and in a second step to fulfill a demand. And we decide that we also need storage for this commodity to reach a higher optimality in the system. And this question for optimality is the discussion of the next slide. So what does it mean to reach an optimal energy system? So the optimality is defined by the objective function. So typically we work with two objective functions. The first objective function is to minimize the CO2 emissions of the system. And the second objective function is to minimize the system cost. And as you see on the left-hand side, just activate the pointer. So we have a kind of funnel which leads to a solution space, and the solution space gets narrowed down with endogenous and exogenous boundary conditions. So for example, one boundary condition which always has to be fulfilled is the energy balance, and exogenous requirements could be, for example, the net zero aim or other restrictions by policy or nature given. And this then leads to a smaller solution space. And within this solution space, based on the objective functions, we find the optimal solution for each of the objective functions. So this leads to a solution dilemma, where we then have Pareto optimal solutions, for example, cost on one axis, CO2 on the other axis. So often we cannot, the cost optimal system is not the CO2 optimal system. And this then leads to this trade-off solutions, which is given by the Pareto front. Okay, so then the connection to the layer above, so we can then give feedback from our energy hub to, for example, if we consider district energy system platform, we can give feedback back to the level above, the city energy system, or we can then set another requirement to the platform below, which Michael will later introduce in detail, to the building and equipment platform, where then we go into a lower level of abstraction and into a refinement process. Okay, what are benefits and limitations? So we have, with the MIL method, we have perfect foresight, which is, of course, a benefit over reality, where we don't have this perfect foresight. So that's why we also have to always consider that in the result interpretation. And we do capacity and operation optimization of technology candidates in a holistic way. So it's not a sequential solution. And typically, as already mentioned earlier, we have the application from building to national and even larger scale of the MIL method. Maybe some limitations. So as the name suggests, it's based on linear equations. So this can lead to some challenges, which are, if we want to represent nonlinear systems, we have a limited time resolution, typically 1 hour. If we go then into control, into the control of systems, which Michael will go into more detail, then an hour is way too less resolution. And yeah, the solution is always found on the edges of the solution space, meaning we are always looking at mathematical solutions, which are rather at the extreme points of the solution space. So there we also have to bear in mind that the optimal and the best solution might not be the same. Okay, then challenges in the GHOST project. I think, yeah, this is the connection also connected to the next presentation, this connection between the MILP approach and then the equation-based simulation and control models with Modelica. So this is one intermediate or direct connection of tools, but then of course also the further connection of Modelica, which Michael will explain, to the underground, so to the geothermal borehole or aquifer storage integration. Then, yeah, the linearization of nonlinear real-world behavior. So this will certainly be a challenge. Where can we make simplifications, and where do we reach then the limit where we can apply these simplifications? And also the integration of uncertainty can be a challenge. Okay, with that, I thank you for your attention. Give back to Alessandro and then forward to Michael.
Yeah, thank you very much, Robin, for the presentation. So now we've seen how we can use optimization tool at the city level, and now Michael will introduce the next level, so the level which is a bit more detailed of how we can model actually our energy systems.
Thank you for this overview and introduction to mixed interlinear programming as part of the Ehub concept. And I'm gonna explain in this presentation why we do need to do a verification of the result that comes out of the platform layer, where we typically do the optimization with mixed interlinear programming. And then in the next part, quickly explain what Modelica is and what it provides in terms of capability, and then show how such a digitized platform-based design process would look like in the context of a geothermal-coupled energy system. So why verification? So verification is really important because the mixed interlinear programming requires substantial model simplification. So those model simplifications, they are really needed in order for the optimization to be tractable. So they're not necessarily a bad thing, but we have to be aware that those are basically leading to an approximation of the system behavior. And some of the key simplifications here are, like Robin mentioned, that all equations are piecewise linear, but physics happens to be nonlinear in many aspects. Then also the second law of thermodynamics may not be satisfied, because typically in those mixed integer linear programming formulation, there's no notion of actual temperature gradients. And for example, transport equations are not explicitly modeled in there. And one example from our domain is that the heat conduction into a bore field, for example, is characterized by moving kilowatt hours from one part of the system into the subsurface. But this one is not really computed based on the available temperature difference in the MILP formulation, because that would lead to a nonlinear model formulation. So in the MILP part, there's really no notion of temperature gradients in the subsurface, which are important in order to compute how much heat can be either extracted or put into the soil, and also how much heat can be stored in a particular geological formation. Another limitation is also that COP is typically not a function of the heating or the cooling load temperature. You can certainly give a certain COP and maybe also do that on a monthly basis or an hourly basis, but there's no direct coupling to the actual evaporator or condenser temperature, because that will again lead to a nonlinear model formulation. And controls in MILP is really optimal. So it's under the assumption of perfect knowledge of the system and also perfect knowledge of the future. So those are really important simplifications that have to be done in order for the optimization to be tractable. But they may lead to situations where the system performance may not be achieved once those simplifications are relaxed. So verification really checks whether the performance of the system can be achieved if those simplifications are removed. And for the verification, we typically use fully dynamic nonlinear simulation that couples heat transfer, fluid flow, and controls, and perhaps also electrical systems. And because those simulations that we use for the verifications are much closer to the physics, those models could also be used, for example, to size a bore field, because then at that point we have actual explicit knowledge of temperature gradients that are driving heat transfer into or out of the soil, and also on the limitations in terms of soil temperature that may be achieved because of geological reasons. So one approach or technology that we are choosing in our project here is the Modelica standard. So Modelica is basically an open industry standard for modeling of multiphysics systems, and it enables coupled fully thermal fluid flow, pressure, and also realistic control simulation. And it has a pathway then to export models, for example, to support operations. So there are large national and international collaborations ongoing and have been done over the past several years to advance Modelica for the area of building and district energy systems. At the Berkeley lab, together with our collaborators, with other national labs like PNNL and NREL, and also within the BIPSA community, we developed open source repository, the Modelica Buildings Library, that has more than 2,000 models and functions. And that allows us now to look into the performance of different heating and air conditioning systems, including also building loads and electrical systems. And what you see on the left-hand side is just a quick overview about some of the domain that we covered. And on the right-hand side, you see a schematic diagram of a Modelica model. It's a very simple case where we have a thermal load, a room model on the top. Then we have an HVAC system with a very simple fan and a heater. And on the bottom, you see an implementation of a feedback control loop with a proportional integral controller. So this one is really a toy example here, typically of much more complex systems that we are building up with this drag and drop framework that then graphically couples equations for fluid flow, heat flow, and controls. Over the past several years, we built out capability in modeling discrete energy systems, all the way from steam systems, from the first generation to the 5th generation discrete heating and cooling systems. They can also be coupled to electrical models, and we have a variety of templates here available that allow, for example, to model billing load using, on one extreme case, a very detailed energy plus envelope model. As an intermediate step, we also have reduced order models that have been implemented, or we can feed the loads in terms of time series. There are also energy transfer stations available, different network topologies over one-pipe reservoir network, for two-pipe system, four-pipe system, and steam system, as well as different storage technologies that can be used within this context. So on the right-hand side, you see now a implementation of a schematic diagram of such a district cooling system, where we have a central plant and a distribution network and the billing load. So why do we care about this type of model resolution here? So that's shown on an example here where we compare the bidirectional network with a reservoir network. So the bidirectional network has the property that it can be shown from an exergy point of view to be optimal, because there is no mixing happening in those two pipes, and the warm pipe and the cold pipe. But they also provide significant control challenges to keep stability of these different energy transfer stations because of the tight coupling here via the pressure in this distribution network. The reservoir network, on the other hand, is from the thermodynamic point of view not as favorable, but it is very easy to control. And the question here was really, can we get the similar performance with the more robust reservoir network as can be achieved with a bidirectional network? And one insight here from that study was that it really depends very much on detailed design choices. For example, how distribution pipes are being sized, how the control is being implemented. And in our study, we started, for example, with energy consumption that we normalized to 100% of the bidirectional network. When you switch to the reservoir network, we had significantly higher energy consumption. But then by improving the pipe sizing and adding dynamic controls, we were able to bring down the energy consumption to the same level as the bidirectional network. So a key question is really, how do we ensure that designers actually build this system with the right control implemented, rather than one of the other variants of this reservoir network that has significantly higher energy consumption, so around 20 or 40% here. And that's where the digitized workflow here comes into play, that we integrate within the platform-based design process. So typically you would start with a master planning that sets very high-level requirement, for example, no use of fossil fuel in this neighborhood. Then in the next refinement, we would be doing an architectural optimization, so using the approach that Robin Mutschler just presented before that, with, in this case, with mixed integer linear programming. In the next stage, we go then into the refinement, where we do the nonlinear system simulation with the coupled energy system and the controls. And then using this control representation, we can then also export control logic and also semantic models with emerging ASHRAE standards, so ASHRAE standard 223P for a semantic model and standard 231P for control logic, so that we have a fully digitized workflow and can be assured that the control logic that we implemented and tested in simulation can be implemented on native control platform via a process that we standardize via ASHRAE and have been developed at the Berkeley Lab with our partners within the Open Building Control project. So that concludes my presentation, and I think I give back the control now to Alessandro.
Yeah, Thank you very much, Michael, for the overview of Modelica. Now we have the last speaker of today's webinar, Alireza, who will give an introduction and an overview about the pilot sites and the case studies that we are using in the GHOST project.
Thank you, Alessandro. Do you hear me?
Yes.
Do you hear me? Yeah.
Yes, yes.
I will present in Work Package 5, actually, that it is a focus on implementation of a case study. Let's see here if it works. And Work Package 5 actually aims to calibrate, validate, and demonstrate the platform-based design framework's novel and scalable methods and system and technology. Activities will take place across 4 pilot sites with varied location and scales, ending in demonstration in 5 different cities through the case studies. The pilot sites are located in 4 countries, and is United States, Switzerland, Australia, and Denmark. And case studies are located in 4 countries, USA and Switzerland, is 2 cities in Switzerland, and Germany and Australia. And 1 project is in a building school, and 4 at the neighborhood school, and 3 at the city school. We have in this project, we have a Work Package 5. We have actually Work Package 5 is made of 3 tasks. And task 1 is about making sure that the test and study sites follow the law and getting them ready to check if the models of the sites work well. And the goal is to make sure that what's happening at these sites is legal, and to gather important information about the building and system that are already there for a complete first checkup. In Work Package, the task number 2 in Work Package 5 is about collecting information from test sites to make sure that the geothermal energy models and energy system design work as expected. It is also about checking that the design method is easy to work with, and that's what it is supposed to do. This includes creating virtual model or digital twin of the sites. Additionally, they will set up computer system to handle all the data they gather properly. And the last task is actually showing how the platform-based design framework can be used in real-life projects to find out where geothermal energy can be used in cities, and to help design energy systems that work well with this type of energy. The task also look at how this can be added to places that already exist, making sure it fits with what was planned in an earlier part of the project in Work Package 3. Required input is model software and tools, all formatted for integration with the pilot size operational management system. And additionally, a use guide for the platform-based design framework and its tools is provided. Regarding to put the platform-based design plan into action for the studies, leaders will team up with different people to make sure everything follow the laws, and they will gather all the necessary information to get a complete picture of what each place is like now. They will note down specific about the heating, cooling, and underground heat setups, and along with any tools, computer program, and managing building, computer, communal, heating layout, and other devices. They will look for and keep any existing two-dimensional and three-dimensional model design of the place that they are testing. Here I want to show some pictures of the pilot sites. Here you have Empa campus that's involved in the project, and they have a building area of 6,000, close to the 61,000 square meter, and the annual loading is 6.8 gigawatt hour for heating and 3.5 gigawatt hour for cooling. Here we have a pilot site from Denmark called the Bispebjerg Hospital, and it is a building area of 165,000 square meter, and annual loads demand is 5.1 gigawatt hour, and for a heating and for cooling is a 3.8 gigawatt hour in this site. For another pilot study is from Berkeley campus, United States, and building area is here much bigger, is 1,170,000 square meter, and annual electricity use is 258 million kilowatt hours. We have also another pilot site in the building school, and it is a school, Enkplatz, and is from Vienna, and they have a building area of 7,880 square meter. And here is the city level, is a Vienna, and we have an area of 415 square kilometers. And here we have again from Berkeley, and it is a city level also, or city scope, and area is 45.73 square kilometer here. And city of Zurich also we have here, and area is 87.88 square kilometers. And the last one is city of Geneva, no, the last one is this one is a Freiburg from there's a district level, and is a 560,000 square meter that we are talking about. Thank you for your attention. Thank you, Alessandro.
Thank you very much, Ali, for the presentation. So I cannot see any question here at the moment. If anybody want to ask any questions, just write in the chat. But in the meanwhile, maybe I can just start a quick discussion. Maybe I was actually wondering if Emil maybe knows something about the geothermal market in the US also, or if your company is, of course, I believe that is mainly focusing on Europe. But do you know any numbers about the US or North America in general? Since we have also partners from the US in the project, of course, it would be interesting to know if you know anything about that.
Alessandro, I have not concrete numbers here at the moment, but we have a section in our market report which is also dealing with the rest of the world, and of course a big part is also on the US. As far as I know, recently with the Inflation Act, they put a lot of money to develop renewables, and also in comparison with what Europe was doing, we saw that the amount of money that they put was quite huge for all renewables. So they are really developing at a larger scale than in Europe, and geothermal is also a part of that. So they have great potential, being sort of a continent themselves. But yeah, maybe also I can later on provide you with some more specific numbers also taken from our analysis on the market report.
Yeah, thanks.
Emil, it would be fantastic if there's a comparison between Europe and the US. It would be really helpful for us also to argue where these two continents are.
Yeah, well, the kind of data that we have is more general data. It's quite difficult for us also to have specific data at European level. So we don't have this granularity for the US. We mainly try to have sort of comparison of the framework and the kind of investments that they have there. So we don't have such a granular data for the US, but of course it's always interesting to see what's happening in the rest of the world. And usually, yeah, we have also other section talking about other countries such as Japan or Kenya or Indonesia, countries which have also quite an history with geothermal, especially the last two.
Thank you.
It would be certainly interesting to see a comparison also in terms of the investment and policies across the different continents. For example, in the US, there is from the Department of Energy the enhanced geothermal Earthshot that tries to reduce cost for electricity generation by about 90% by 2035.
Yeah. And then also I wanted to ask to Michael about the Afshari standard, because I know that Afshari is mainly focusing on buildings, but are they also developing a control standard at district level?
Well, the digitization that I alluded to in the presentation, that's not restricted to buildings. So it can also be used for district energy systems. So a lot of the development in control logic, for example, guideline 36, that's developed by Ashby, that's for buildings. But the underlying digitization framework is agnostic, whether that's applied to a subsystem of building, a whole building, or a district energy system.
Okay. Okay, so it doesn't matter if the scale, so it's not important the scale, but these control logics can be applied to any kind of system. Okay, interesting.
Yeah, so not the logic itself, but the digitization underneath the technology. But the control logic, the sequences, they will then be, of course, different if it's a particular district energy system, but they can be implemented using the same technology and tools and then exported digitally using the same workflow.
Yeah. Okay. Thanks. Something else? Some other questions or comments?
Yeah, but I'm interested also again for if we have Emil on board with his view on Europe. With your expertise, what do you think is the major challenge, or what? No, put it the other way around. What are the hurdles that the geothermal potential is not really used, or it's not fast accelerating in Europe? So it's always, yes, there are interesting projects, but it's not like on scale, something like that. But what is in your mind the largest hurdle for that?
Well, I would say, first of all, seeing a bit also the being next to the European legislator, we saw that one of the big initial problem was for the legislator to get to know actually the geothermal sector and the geothermal potential, which was not always the case in comparison with our other more, let's say, mainstream renewables like wind and solar. So a first initial effort is really to be to have the right narrative of the geothermal sector, and especially because the few people that knows something about geothermal, they usually think that is something strictly related to specific areas of Europe, such as islands or Tuscany, etc. So the first big effort will be really to showcase all the potentiality of geothermal, the different technologies that there are around geothermal. Second thing I would say, we have a problem of resource mapping, which is key, especially to develop big projects around Europe. So an effort should be done at member state level, but also maybe at European level in order to better organize this effort. And then, of course, the issue of the upfront cost and how to deal with them. So, for example, as AGEC, we try also to push for risk mitigation schemes around Europe. We try to showcase which are the best example of risk mitigation schemes at national level, and maybe also in the future to propose one scheme at EU level, because this is key. We have, for example, the example of France, with thanks to the knowledge that they have of the Paris Basin, they can finance a lot of drilling around France and keeping it sustainable in terms of cost to try to explore other areas of the countries in terms of geothermal potential. So I would say these three things to start off, which will be already a lot, because get to know the sector, having the right map of the ground and having the right tool to deal with the upfront cost will be more than enough to start develop more the geothermal potential, I would say.
I think we have one question here. I don't know if you can read it, but it says, how do you think about drilling cost or other cost impact on the economic modeling of geothermal feasibility? So I think maybe the question is about the impact of drilling cost, yeah, in general on the economics of geothermal systems. I think, Emil, probably you may know.
It's linked to what I was saying. A major part, in percentage also, of the total cost, and this is why we need, for example, as I was saying, tools like risk mitigation scheme, because it's not only that the cost of actually drilling, it's also the fact that maybe once you've drilled, the geothermal potential that you found is different from the one you expected before, and you can have different, let's say, range of success in this sense. It can happen that you have very few potential, or that the potential is still quite good, but different from the one that you were expecting. So the whole business model has to be redrafted in a sense, and this can be problematic. So it's a combination of various factors, knowing better the ground, having the right tools to deal with this cost, and also maybe have develop also some business models that, for example, put together private and public sector as well. We have good examples, for example, of private and public partnerships around Europe, in which sometimes there are municipalities or local energy suppliers that also invest or are part in dealing with the construction and of for example, a district heating plant. So it's also important to make it appealable from an economic point of view, from private investors and also to consumers, because it's also quite important to convince citizens, the people, that geothermal is convenient for their heating and cooling choices, for example, and that is more convenient than other solution, renewables or not renewables, and that in the end it pays off.
But the interesting point, Emil, are convenient for consumers. In Switzerland, we have this big discussion about deep geothermal drilling and causing earthquake, so that people are not really even willing to actually accept these drilling initiatives. Or so is that just a Swiss problem, or have anybody even from the panel observed that in other countries as well?
Of course, also this issue of acceptance is something that the whole sector has to deal with, because there will be a couple of technical problems in the past, but this is not the point, in the sense that geothermal is really secure technology. So it's all about information and having the right answers to the right questions. So of course, people, it's good that people pose themselves some key question about, for example, environmental impacts, etc. But the whole sector has also the right answer to give, so it's not risky for the people. Of course, the important thing is to have the right assessment, also from the right agencies, like environmental agencies or water agencies, which is something that it's already happening. So every time there is drilling, there are also different agencies that are assessing the fact that everything is secure. But indeed, this is another thing to take into account. It's not only about money, business models, but it's also about convincing people that this is the right choice for them and for their community.
Thank you, Emil. We have another question from Nicholas. He is asking how we can implement our tools in practice, because he sees this as a challenge. Of course, how we can really try to make these advanced tools more common in practice in the industry or in companies. So I don't know if maybe Michael or Matthias maybe can answer to this.
Yeah. So the question is really whether goes also focus on modeling geothermal heat for direct use for cooling, so without the compressor. And to say that the tools that we are developing are certainly applicable for that as well. So there are the different levels of resolutions that we are using for the subsurface modeling, but all of them basically include then dynamic heat transfer and characterization of the subsurface temperature, and through that, the temperature that comes out of the borehole via the piping system. And the tools also allow then coupling that to energy system model and the building models. And we released, for example, just I think 1 or 2 years ago, a simulation study that shows resilience benefit of geothermal-coupled district energy system, in which case we had a scenario where we provide cooling with a compressor during a normal operation and also heating with heat pumps. But then during a heat wave, when we have to shed significant electricity consumption, we actually switched off the chiller and used direct cooling using the temperature that comes out of the borehole, and coupled that to a detailed energy model of the energy system in Modelica and the building envelope in Energy Plus, with the spawn of Energy Plus coupling. And through that, we are able to show what happens to the room air temperature and the overheating in the office buildings if we only provide direct cooling from the subsurface. And the same technology can also be used, and for example, to size subsurface heat storage or geothermal heat exchanger in climates that would allow direct use for cooling. For example, Central European climate, where you often don't have the problem of having to dehumidify the air. So you can use those the same models and see what's the potential in terms of providing certain level of comfort cooling without any compressor, by cooling down the soil in winter when you extract heat with a heat pump, and use that afterwards for cooling in summer.
And may I just add on that? As you see, you can do all this, use these sophisticated tools to do better decision making. And of course, now you ask, how the hell these tools are really accepted by industry as well? And just thinking back, when they introduced Excel. So I was at the time studying when they introduced Excel, and they told us, ooh, these tools, they will actually replace engineers. So we can do everything on that, and it is really strange. And even if they started off to doing macro programming on Excel, and says, this is much too complicated, and this can't be actually done just by some PhDs and all these kind of stuff. And today, Excel or even computer-aided design is used as a tool. As a tool are used by everyone, and the tool is as good as the user is. There's not a vice versa. And we think exactly the same happen right now, that we are switching in the engineer sector from doing linear processes, from basic design to detailed design to construction. What you do right now, or what we see the movies now, that engineers are trained to use actually models. And they build, if they have a question, they build models, as Michael mentioned, and you can ask different questions on these models, and you get answers which are more profound, where you can do better decision making. And so we see actually also this diffusion of these models into industry, and it's a bit shaky, of course, because you have to adjust your workflow. But we see also a strong development in the educational part of engineers. Today is when you go at university, and maybe Ali or Alessandro, you know that as well. If you have a problem, students get straight into Python and try to actually model the problem and getting the answers. And this is exactly what the engineers in the future will do, because these trained people getting into industry and will use models.
Thank you, Matthias. Yes. Robin, you raise your hand.
Yeah, I just also wanted to add on that. I think, Matthias, nowadays it's more ChatGPT compared to Python.
I'm not happy with the ChatGPT. Robin, we just did a simple problem.
Yeah.
Transforming or recalculating terawatt hours in kilowatt hours, and ChatGPT screwed up.
But yeah, actually, this was not my main point.
So it's as good as the users are.
So I mean, I completely agree with you, Matthias and Mike. I just wanted also to briefly summarize what the Ghost project can contribute. I think we have 3 phases. We have the first phase, the conceptualization, which was explained by Matthias with the platform-based design. Then we have a second phase where we validate this concept and we improve this concept with the pilots and case studies, which was presented by Alireza. And then the third phase is then the dissemination of this knowledge. So our aim is to come up with a somewhat as a blueprint where we say, okay, this is a approved method now, which can be applied in a certain way in industry. So we aim then with the experience we gain to make a recommendation also to industry and say, okay, this is how it could be applied.
Perfect.
Yeah. Thank you, Robin. We have 2 more questions about the, does the current capability of GOES focus on modeling geothermal heat direct use for cooling? So I think the question is if we also focus on cooling, yeah.
Yes, absolutely important. Yes.
And then
no, it's most important. So you can't do even on district energy system planning. You have to consider cooling, and cooling. It's not only a matter of fact because of climate warming. It's also a matter of fact that the people wants to have more comfort in their building, and it's driven by comfort and of course also by climate warming. So we have to consider cooling. Yes, absolutely.
Yeah. Thanks, Matthias. And then also a more specific question from Dennis about if we have already an idea about how we can interface the different platform. So from city to building, that's actually the main focus of the projects. Yeah.
It's only the main focus of the project. We outlined some ideas and first approaches in the paper that was cited in Matthias' presentation, but again, platform-based design is really a process framework that can then be adapted to a specific problem, whether it's the design of a particular energy system, or going back to the discussion we had earlier about the first cost of a geothermal system that's relatively high. We could also envision, for example, using the framework of platform-based design to look at these cost implications on a city or nation scale, because you could argue that if you put in geothermal system, you're gonna have a lower peak electricity consumption for heating and also for cooling, because the heat pump in heating mode can harvest heat from the subsurface, which is at a higher temperature than the outside air that the air source heat pump would be doing, and vice versa for a chiller. So with platform-based design, you can then look at this different level of abstraction and also partition it, for example, into the thermal system and the associated electrical system. And through this framework, for example, have thermal engineers work together with electrical engineers to see if we reduce now this peak electricity demand, how much can we delay upgrade of the electrical grid because of the reduction of the peak load? And what are the economical costs to the society for investing into geothermal system, but through that the delay upgrades into the electrical system, because it's not as much stressed during those extreme heat waves or cold snaps. So that really, depending on the question, the type of feedback that we will have between the layers and the arrangement of these layers can change, because it's somewhat problem dependent.
And as I know that Dennis is a mathematician, maybe I can put that in a more formalized answer and say, yes, we connected already some platforms. Michael mentioned that, like this control descriptive language, these Esri standards. So we connected Modelica then to the operational platform where controls can be specified. There's already some ways or like some connections which are evolving, and we right now doing MILP into equation-based models. And the way to go there is also great work from Michael, generating templates of Modelica level, which can be abstracted, or this is what we have to do, or mapped then to a MILP model. So we think the way to go there, of course, it has to be semantics, has to be solved, but the framework on the level of platform-based design and the tools between Modelica and MILP might, or it looks like, there'll be templates.
Thank you, Matthias and Michael. Robin, you wanted to say something on this?
Yeah, again, I completely agree with Michael and Matthias. I just wanted to add on the last point. So yes, this is the scope of the project, and this is now actually happening at the moment, this definition of the interfaces. We are also having then the workshop in March. So this is a consortium internal workshop, which I think you will attend, Dennis, at KIT, where we work on the definition of the interfaces.
And then we have two more questions. One is probably for Robin. Is there a way to partner or work with the GHOST project? I
think it's mostly for you, the question, but yes, there's a way.
Absolutely, absolutely, absolutely.
So yeah, everyone can join as a observer of the project.
Observer,
yeah.
So we have
even if it is aligned with some tasks, we can also actually connect and extend these tasks. So it depends if you're coming in from the academia side, we can do side projects. We can also integrate projects. If you come from industry side, you're more than welcome to bring in your expertise from the industry side, and just write an email to Alessandro, Robin, or myself, and we will organize that.
Yes. And then one more, can the GHOST project also accommodate what kind of geothermal technology is used? For example, closed loop or other thing. Yeah, I think any kind of geothermal technology can be applied into the platform design framework.
Yep.
Yes. So there's no any limitation in the technology that can be used in the whole framework.
Platform-based design, it's a generic framework, and it comes completely from other industry, like from semiconductor. It evolves into other industry. Most popular, most renowned industry was the automotive industry. And our work is now to bring that into energy systems, but it can be in a domain, just like with deep geothermal systems, or like what we do right now with more shallow thermal systems and connecting that to the urban levels. Yes, you have the freedom to apply and design these platforms according to your system boundaries.
Yes, thank you, Matthias. Any more questions or comments? No?
Thanks.
So yeah, I would like to thank you, everyone, the speakers and the attendees. So I think it was a great webinar. And yes, so you can follow us on LinkedIn, or you can just drop us an email, especially for who wants to partner with us in some way or to work with us. So you're very welcome. Okay, so thank you all. Bye-bye.
Thank
Thanks.
you. See you.
See you.